All right, so we'll start off with part A. Let's read the problem first. It says, let f be a differentiable function defined on the interval from -5 to 6. Figure above shows the graph of f prime, so we're looking at the derivative graph here. F prime has a horizontal tangent at x equals -3, so there's a slope 0 here. Area of the region between f prime between -5 and -1 is 5. Fill that in. F prime is a piecewise linear on the interval from -1 to 6, so these are all linear graphs. Function satisfies f of -1 equals 3. Okay, so we may use that later. Part A, find the absolute maximum value and the absolute minimum value of the function between -5 and 6. Okay. All right, so absolute max, absolute min, we know we have to involve extreme value theorem. So we have to test endpoints and critical points. Right. But let's create a f prime sign line just so that we can kind of have some idea as to where the relative max, where the critical points are. So here's my f prime sign line. We'll extend from -5 to 6. Those are our endpoints. Okay, I like to label my f prime graph. Above represents positive slope, and below represents negative slope. On the x-axis is where my slope 0 is going to occur. So my critical points will just be at -1 and 2. Above the x-axis represents where my original graph is going to exhibit positive slope. Below the x-axis, negative slope. And then 2 to 6 above the x-axis again, positive slope. So we know we have relative min at 2, we have relative max at -1, so all 4 points are points we want to be testing to determine max and min. So I do need to involve, if I want to find these points at f, I'm going to have to involve my position formula or my final destination formula here. So as a reminder, anytime I want to look for a final position, it's going to be my initial position or given position plus displacement. So x of b is equal to x of a plus the integral from a to b of f prime. Okay, so we have our endpoints and critical points. So we have to test all 4 points. Let's start with -5. So if I want to find f of -5, I'm going to start at what's given to me. I have f of -1. And I need to bridge the gap between -1 and 5. I want to know how much progress is made between these 2 points. So integral from -1 to -5 of f prime. Maybe it'll help if we just go ahead and find the area of the regions that we need for each of these values here. So let's see, between -1 and 2, we have 1/2 base times height. So that's 3 times 2, that's 6 divided by 2, which is 3. So we know this region is -3. Oh, 3, yeah. 2. Between 2 and 6, this area is all just going to be another triangle here, 1/2 base times height. So 4 times 4 equals 8. All right, so we're going to find, I think we have enough information to fill this in here. But the issue right now is that the integral from -1 to -5 is kind of backwards, right? But we definitely need to start here because we're starting at -1 and we're ending at -5. But it's easier to read if we're not having to look at this backwards. So I'm going to rewrite this as minus So the integral from -5 to -1, that's going to be a +5. We can insert +5 in here, but make sure we have a minus there. Okay, so we have a location for f of -5. And now we'll seek out the locations for the others. So let's find f of -1, going through the same process here. Well, the nice thing is f of -1 is already given to us, so not much effort there. Now let's test my other critical point, f of 2. So f of 2 is the initial starting point, which is always going to be f of -1, plus, and then how much progress I made between -1 and 2, and that's just the area under the graph. Between -1 and 2, we see that region is -3. This is from going from smaller to larger, so there's no need to adjust the bound there. Okay, so f of 2 is 0. Finally, our last endpoint, f of 6. We start at f of -1 again, plus the integral from -1 to 6. So 3 minus 3 plus 8. All right, so we have 4 values to compare. We want the absolute max, which is going to be the highest y value, and the absolute min, which is going to be the lowest y value. So I'll move this over here. Any questions with part A?
How did you decide on the intervals?
Oh, let's see, the intervals. You mean -1, 2, and 6?
Like in the actual integral notation, like from -5, -1, or -2, -1 to 2, or.
Oh, got it. Right, because we're following this formula here. So the formula says whatever my starting point is, that's where I want to begin. And wherever my ending point is, that's where I want to end up. So if I'm looking for f of 2, I'm going to start at f of -1 because that is what's provided for me. Whatever is provided for me, this is my initial point. So for instance, if I want to find f of -5, that's my b value. And I'm given f of -1, so -1 is my a value. So if I want to figure out my integral, it's always going to have to follow the path of starting to endpoint. So these numbers will always match, and these numbers will always match. So same values there, same values there.
Okay, that clears it up. Thank you.
Okay. And then we just rely on our graph to determine what the area or the displacement is for that region. Okay, part B. Write the equation of the line tangent to the graph of x when x equals 5. Use the tangent line to approximate f of 5.1. This is linear approximation. So as a reminder, linear approximation steps. First thing, you want to find the slope or find the point, find the slope, and then write your tangent line equation. So really, if you can write your tangent line equation, then most of your work is done. And then once you have your tangent line equation, then all you do is you just dump that decimal value into the equation. So we want to find the equation of the tangent line when x equals 5. Well, we have our ordered pair. Well, actually, we don't. We have to find our ordered pair at 5. So we need to find f of 5. So to find our ordered pair, we're going to rely on our formula here. So my starting point is 3. And then the accumulation of the region between -1 and 5. So I have to go from -1 all the way to 5. But the thing is 5, we may need to figure this value out here. So that's right at 2 here. So this is 1/2, 1 times 2. This is an area of 1. If that's an area of 1, then we know this entire triangle is 8. We know the remaining region must be 7, right? So if I want to find the depth integral from -1 to 5, from -1 to 5, it's just going to be -3 plus 7. All right, negative 3 plus 7, which is 4. So 4 plus 3 is 7. Okay, so that's my order pair. To find my slope, I need to find f prime of 5. Well, this should be easier because the graph that we have in front of us is the f prime. So f prime of 5 is just the order pair, so f prime of 5 is right at 2. Okay, there's my order pair, there's my slope. Point slope form. Get y by itself. Now we have our tangent line equation. We just plug that decimal value into our equation. So 5.1 will go in for x. So 2 times 0.1 is 0.2 plus 7, 7.2. There's our linear approximation.
Can you go over where you found the slope from again?
Sure. So slope is f prime of 5. So this is the f prime graph. So f prime of 5 is just going to be the order pair here. Does that make sense?
Yes, thank you.
Okay. All right. Any other questions with part B? All right, let's go to the back, part C. Part C says g of x is defined as the depth integral from 3 to x of f prime. Find g of 3, find g prime of 3, and find g double prime of 3. Okay, so g of 3 is just going to be involving the area under the graph. G prime is the derivative of g, which is really at the f prime level. So I want to show that I want to show where g of x, g prime, and g double prime is coming from. So if g of x is this expression, then it's understandable that f prime is really sitting at a level below g, right? Because an integral applied to f prime is going to make it the same level, right? So integral of f prime pushes this expression to the same level, which means that f prime originally is sitting at a level below g. So really f prime is at the g prime level. But I want to show using second theorem here. So if I want to find the derivative of g, that's essentially saying, well, I'm going to involve the derivative of this expression. And seeing this as a reminder that there's second theorem going on here, we can undo these two processes. The upper bound gets inserted in for the t, so we're just left with f prime of x. So our g prime is at the f prime level. G prime is the f prime. which means that G double prime must be at F double prime. So we're just making both apply their derivative process. And this is just so that we can see that relationship between G and F. So when they ask for G of 3, G prime, G double prime, we know how to look at the graph. We know that relationship there. So we have everything related now between G and F. Now let's find G of 3 first. So G of 3, we're just going to insert 3 in for the x of our integral. The convenient thing is that the bounds are the same. If the bounds are the same, there's no area for us to find. It's always just going to be 0. If I want to find G prime of 3, then I simply rely on this, F prime of 3. And F prime of 3 is just the order pair because this is the F prime graph. So F prime of 3 is just that order pair, and that order pair is sitting there at 2. And now we want to find G double prime of 3, which is F double prime of 3. And if this is the F prime graph, then F double prime must be the slope, right? And so the slope of this F prime graph at 3 is just whatever the slope of this line is. And if I know that I'm starting at 2 and I'm going up to 4, so that's up 2 units over 1, that's the slope of 2. Okay, so that's all for part C. All right, last one here, part D. Evaluate the limit. This is a funny looking limit problem, but it's a real number, so we just enter that 2 in to see what we get in return. So if I enter 2 in, I get F prime of 2 over e to the 2 minus 2 minus 1. So F prime of 2, we know that this is the F prime graph. We can just look for the order pair. F prime of 2 is just going to be 0. So numerator is 0. Denominator, 2 minus 2 is 0. E to the 0 is 1. 1 minus 1 is 0. So we have 0 over 0. This is not something that we can factor, but we can find the limit. There's a hole in the graph, but this is also a condition where we can apply L'Hopital's rule. L'Hopital's rule says I can find the derivative of the numerator, take the derivative of the denominator, and then I can reevaluate the results. So let's find the derivative of each of the numerator versus denominator. Numerator, f prime, if I want to find the derivative of f prime, that's going to push it down to f double prime. The derivative for e to the x minus 2 is just e to the x minus 2 times 1. Right? As you recall, the derivative for e to the u is just e to the u times u prime. So therefore, e to the x minus 2, which is going to be e to the x minus 2 times 1. Careful, this negative 1 is also being impacted by the derivative, so that's going to go to 0. So now we have a simpler version of our limit expression. Now I'm going to reevaluate, and the hope is that this will turn into something that's a real number instead of a 0 over 0 from before. F double prime of 2. This is, well, it's asking for the slope of the graph at 2. And we saw from before that this slope is 2, so we know it's going to be consistent here. This is also a slope. This whole line is going to be a slope of 2. E to the 2 minus 2, that's e to the 0. Anything to the 0 power is 1. 1 times 1 is still 1. So we're able to arrive using L'Hopital's rule, a real number, and that's our limit. Okay, any questions?
Just for part B, is the
Yeah.
final answer to that whole question just 7 or y of 5.1 equals 7.2?
That's right. Yeah. It says use the tangent line to approximate f5.1. So we take the tangent line and we dump the decimal in, and whatever value we get back in return, that's the approximation of the line, approximating the graph on, approximating the point on the curve. So it's not exact, but it's the method that they're asking us to approximate that point. All right, any questions? Miriam, any question?
No, I understand so far.
Okay. Well, I hope to have more help sessions going over homework 8 and 9. This is homework 7, so if you did this, you just just did it along with me, so that's good. Homework 8 and 9, I'll figure out a help session for those, but if you can't attend it, I'll record them. So, all right, hope you guys have a great weekend. I'll see you guys on Monday.
Thank you so much.
All right, thank you. Bye. See you. Bye, Miriam.